Good evening, everyone. On behalf of Triple IT Kottayam, I first want to welcome you all for the Q Thursday webinar series. And let me introduce you to this wonderful Quantum Thursday webinar series. And the program basically aims to provide you all a flavor of quantum computing from different experts of different domains. And to start with, we have Dr. L Benkata Subramaniam from IBM. And whenever we say quantum computing, I think it's a great opportunity to start with an expert from IBM. And because they have been contributing to this quantum computing a lot. And we have a series of 5 sessions in this quantum webinar series. You might have already seen 3 of the experts in the other poster that we had. So actually it will be a 5 sessions, and it will be like weekly. Every Thursday we will have one session, like so you can fix up your time for just in the evening 5 to 6:30 every Thursday up to February last week. And I hope you all will have an enhancement in the knowledge of this futuristic technology. Thank you all once again for taking time to join and experience this. And thank you, Venkat, for accepting immediately to this, and thank you so much for joining our session. And yeah, that's all from me, and that's about the overview. And I hope I will see all of these participation and all of the support throughout the webinar series throughout every week. Thank you so much.
Thank you very much, ma'am. It is my honor to welcome today's speaker, Dr. L Benkata Subramaniam. He is an IBM Quantum Ambassador and leads the AI reasoning and quantum computing teams at IBM Research India. He is a strong researcher who has developed new products and published in top venues and has been recognized as a master inventor. His current goal is to set up quantum computing as a leading area of research in India. A very hearty welcome to you, sir. I request the audience to keep themselves muted. Questions may be asked in the Q&A session towards the end. Now, without further ado, I welcome Dr. Subramaniam to start the session. Over to you, sir.
Thank you so much. Thanks, Professor Lincy, for having me over. Thank you so much. So today what I'll do is, so this is the first session, and okay, can I start sharing? Yeah, so I'll go through the basics. Okay, so what I'll do is I'll go through the very basic things about quantum. Okay, so maybe for some of you it might be you might already know some of these things, so please bear with me. I'll try to cover more ground here so that you get a introduction to how quantum is evolving. What are the applications that we are looking at? How is India placed in quantum? And how across the world things are evolving, right? So before I start, so I'll start by asking you some questions. Okay, so I'm going to place a poll here. Okay, can you please see my screen? It says www.menti.com. Can you go to menti.com? Are you able to see the top?
Yes, sir, it's visible.
Okay, great. And once you go to Menti, you have to enter that code. Okay, so there is a code there, that number, you have to enter it. So so the question I want to ask is, what words come to your mind when you hear the word, when you hear this quantum word, right? So what comes to your mind, right? So some word or phrase, whatever comes to your mind, just write it. I want to see what you think about quantum, right? Okay, so we have some physics, strange, exotic, okay, faster processing, low temperature, quantum physics. atomic calculation, Erwin Schrödinger, yes, Schrödinger's cat, very famous. Qubits, light particle. Okay, so very interesting. I see a lot more technical audience here, because when I ask this question at other locations, there are other things, this looks like a very technically intelligent crowd that I'm talking to here, because you're going deep into the physics of it, so small entity, light particle, low temperature, disrupting cryptography. Excellent. Okay. Packet, futuristic, waves, 1, 0, and in between state. Okay. So looks like I don't even have to give a lecture here, because this word cloud here covers everything. Okay. So I'll go back. Okay. There are still some coming, right? So I'll wait. Complex. Okay. I don't know. Madhu. Okay. Somebody, is that somebody's name, or Tarun? Okay. I see Tarun, Kumar, Madhu. Okay. Okay. And I hope Tarun, Kumar, and Madhu, you also make great contributions to the area of quantum computing. Okay. Excellent. So I'm going to go back. So today what we are going to talk about is, how do you prepare for the quantum era, right? How do you, as a student, as a faculty, or a software engineer, what is it that, what's the quantum era? How are you going to get ready for it? So that's what this talk is about, right? So quantum actually involves a lot of different technologies. So there is quantum cryptography, there is quantum computing, there is quantum sensing, and there is the hardware aspects of it, the physical quantum computer. Then there is quantum communications. So there are multiple, things. When you talk about quantum, there are several aspects of quantum. And today I'll focus more on the quantum computing aspect, right? I'll give you some indication of where the hardware is heading, how cryptography is evolving, but more or less the focus is on the quantum computing aspect. So the first question, are quantum computers faster? Okay, so there are many of these, cartoons that are all over the place, right? So like this one. So I want to ask you this question, right? Do you think quantum computers are faster? So I'm going to go back here. Yeah, now please, again, the same site, same everything, same code, and you'll see a new here. So I see votes for quantum computers, nobody so far for classical. Okay. So everyone, okay, I see 1, 2. There are some people who think classical are faster too. Okay, great. Okay, so quantum is well ahead, but there are some people who are going for classical. So more than 2/3 of the people have gone for quantum, but there are some for classical also. Okay, so now this is a very important question. Okay, so I want you to remember this question, and I want you to keep thinking about the answer that you've given to this question, right? So, okay, so let's go back to our presentation, right? So the majority of maybe like 3/4 have gone for quantum computers. Okay, so there are now let's look at what are quantum computers faster. Are there things they are faster at? Are there classical things that are faster? So I'm going to start with, the simple operation of multiplication. Okay, you're multiplying P and Q. So let's take two large integers and multiply them, and you want to find the result. So what is P into Q? So the cost on a classical computer will be 0.0 fraction of a second, and on a quantum computer, the same operation takes over a minute, right? So we'll get back to the speed aspect in a more rigorous way, maybe little bit more. But the simple operation of multiplication we are seeing is faster on a classical computer. Okay, so there are things that classical computers are faster at. Okay, they are much faster at. Then now let's look at another operation. Okay, so let's now look at, you're given a large integer n, and you want to find its prime factors p and q. Okay, so take a large number and find its prime factors. So how long does this take on a classical computer? This operation will take you billions of years. Okay, so this is the basis for a lot of the cryptography that we do today. Okay, so a lot of the cryptography online, whether it is bank transactions, whether it is encrypting the data that you're storing or transmitting, a lot of this is based on the fact that classical computers cannot do factorization fast enough. Okay, so that's the whole basis for cryptography today, right? The same operation on a quantum computer will take much lower amount of time, just a few hours, right? And this is a famous algorithm called Shor's algorithm, which showed that quantum computers can do factorization in polynomial time, right? So that's the whole basis for this is built on that. So here is an operation which quantum computers are faster at, right? So there are things that classical are faster at, there are things that quantum are faster at, right? So what does that mean? That means that industry workflows or any workflows that you have will involve quantum processing units, it will involve GPUs, and it will involve CPUs. And everything today is available over the cloud. So industry workflows, we are seeing more and more that they will be hybrid. They will involve both quantum and AI. Okay, and that's how the change in the businesses is going to come with quantum computing. You're going to see some of the workflows moving, or part of the workflows moving to quantum. Some of it remains on AI or your traditional infrastructure. And this hybrid infrastructure is what is going to get more and more adopted by the industry, right? But also remember one very important point. Okay, so even though we are saying this, that this classical cost of factoring is 4.7 billion CPU years, that's a fact. Okay, that's true. If you try to do it on any of the fastest supercomputers today, that's how long it's going to take. But the cost of factoring on a quantum, that is a theoretical result today. Okay, so we do not have quantum computers that are going to run any large enough, prime number and factor it, large enough integer and factor it for you. So we are still a little bit far from that time when quantum computers will be doing this factoring and our cryptography schemes are going to break up. But today, this is a theoretical or a mathematical result called Shor's algorithm, right? And so now, so remember that Shor's algorithm. We'll get back to that in a bit. But the basics. Okay, so I saw in that word cloud, a lot of you seem to already know this. Okay, so I'm not going to spend much time on this, but the basic unit of information on a quantum computer is the qubit, and we will see what the qubit is. But the qubit, which is different from the bit, which is on the classical computer, is the basic unit of information. And using these basic units of information, we build, and gates, we build what are called quantum circuits. So when you want to carry out any operation or carry out any program, you're going to write it in the form of a quantum circuit that will run on a quantum computer, right? So that's how, that's the flow today, right? And just to go a little bit deeper into what are these qubits, these qubits have special properties. Okay, so these qubits can be placed in what is called superposition state, and these qubits can be put in a state called entanglement. So what is the superposition state? The superposition, I saw again on that word cloud, some of you already know this, maybe all of you know this, but we'll just revise that. Superposition means that the qubit can be in this state where it is both 0 and 1. So when you toss a coin, when it's in the air, it is both heads and tails. Only when you take it in your hand and see it, is it head or tail, right? So in the same way, the qubit can be in the superposition state until you make that observation, right? So it remains in this, combination of 0 and 1 state. What is entanglement? Entanglement is two qubits can be entangled. So it is more like, I am tossing a coin, you are also tossing a coin. I am sitting here in my home, you are sitting in your home or in your college. I'm sitting at this end of the universe and you are sitting at the other end of the universe. But still, if the two qubits are entangled, then by looking at my coin, I can say whether you got heads or tails. Okay. So when we, entangle two qubits, they interact with each other, and by looking at one of the qubits, you can say what the other qubit is, right? So these are the, the properties from quantum mechanics that is used by, quantum computers, and that's what makes it very powerful, right? So what kind of power does it give it, right? So let's take this maze. Okay, you want to solve this maze. You want to find a path from the center to the outside, right? So how do you do it on a classical computer? So what would you do? You will try out each and every path, right? You'll try path 1, you'll try path 2, you'll try path 3, and you'll try each and every path until you are able to find the path which takes you out, right? On a quantum computer, what you'll do is you will put the qubits into these states where all the possible paths are captured by these superposition states, right? So path 1, path 2, path 3, path 4, path n, all the paths, you put these qubits into these superposition states, and you destructively remove out the paths which are not correct. And what does that do for you? It enables you to very quickly arrive at your answer, right? So today's, this talk, we are not going into any of the mathematics. We're just talking of things in a sort of an intuitive sense, right? We are just covering things intuitively, trying to see how, these basic fundamental concepts work, right? So going back to that cryptography thing, the factorization which we talked about, a lot of today's factorization algorithms will get broken when Shor's algorithm gets implemented on a quantum computer. So today, Peter Shor's algorithm has shown that you can break these. Sorry.
No, sir, it was accidentally unmuted. You can continue. So
Okay.
that person had accidentally unmuted. You can continue.
Okay, no problem. Thanks. Yeah, sure. So so the cryptography of today needs to be protected against the quantum computers. So you want to make them quantum safe. So this is one of the things that scientists are looking at. So as the crypto clock counts down to zero, how do you make your cryptography quantum safe, right? So that's one of the things. And Peter Shaw is a very interesting person. So there was this poem competition, and in that poem competition he submitted his poem that he did not win. So what he did was he put it on his website. Okay, so uh, he and his wife wrote this poem. So if computers that you build are quantum, then spies everywhere will want them. Our codes will all fail, and they'll read our email till we get crypto that's quantum and Daunton, right? So yeah, he wrote that algorithm and also this poem. Uh, so the very interesting thing is that quantum. Here is one example of a very mathematical thing which quantum can do much faster, and which is going to have a lot of practical applications in our world. The internet of today has to completely change. The public key cryptography has to completely change to accommodate or to ensure that your cryptography schemes do not get broken and the data remains secure, right? So that's one example, but what are the other things, right? So here is, here are, hard classical, your classical computers. This is the blue space, right? That's the blue space where classical computers today can do things. But before I talk more about this, I want to go back and give you another question here. So I'm going to, so please, this is the same site, but the code is different this time. Okay, so use this new code 249505549 and just write what you think are good application areas for quantum computers. The code is different, so you'll have to type the new code, but the website is the same. Okay, time travel. Okay, I see a lot of imaginative things also here. Uh, Space has always been a very exciting thing for everyone. Government spying, okay? security, music composition, quantum wormholes. Okay, somebody's been watching a lot of science fiction movies, but yes, maybe in future it will all become reality. Aerospace prediction, quantum AI. Okay, so we have a lot of very nice applications that people think will be coming up, right? So let's look at, the applications that we are seeing today, right? So what are the applications where we are seeing adoption? So before we go there, right? So let's look at, what are the problems which are hard for classical computers. So this blue oval here is the classical computers, and then there are easy problems for classical computers, things like multiplication, things like this video conferencing that we are doing, things like, my voice is traveling over this channel. So all of these are, things that classical computers are able to do very well, right? So they're able to do it in a much easy fashion. But there are problems like these, this light blue thing here. These are the hard problems. So we just saw factorization is going to take billions of years for large numbers, prime factorization for quantum computing, for classical computers, right? What else? So there are other things like in chemistry, materials, machine learning, optimization. Many of these problems which are hard for classical computers, well, there are things that classical computers do. But for example, if you're trying to look at how large molecules interact, or you're trying to find new materials, you're trying to see, speed up machine learning, optimization for large sets of, parameters. So all of these are hard problems for classical computers. And though this dark blue here is what, quantum computers seem to be good at, right? So we just saw that factorization, which takes billions of years, can be done in a few hours on a quantum computer. Well, at least mathematically so far, right? And then there are a class of problems here on this outer edge here, which can never be done on, classical computers. So what are those problems? Things like, simulating small molecules. So the interactions between molecules, that's a quantum mechanical thing. You can never simulate that on a classical computer because that whole phenomena is quantum mechanical. You would have heard about the Large Hadron Collider, right? Miles of this ring where lots of physics experiments are getting performed. You can never simulate any of that on a classical computer because those, follow the laws of quantum mechanics. Whereas you can do it on a quantum, computer, because that quantum computer also follows the same laws that are followed by these, the laws of physics, the laws of chemistry. It's the same laws that this quantum computer also follows, right? So which means that quantum computers can completely change or completely, change the way businesses are run, the way that science is done, to be able to solve, some of the tough problems or some of the unsolved problems, before us, right? And that's really the promise of quantum computers, right? So that's what quantum computers are, promising, and that's what excites everyone, whether it is the industry, whether it is the governments, or whether it is the students who want to learn and enter this industry. But where is quantum computing today, right? So quantum computing is at a stage where the early computers were, many years back. And that's the stage at which quantum computers are. You know, even in the 80s and 90s, when I studied, when we would enter the computing lab or the computer lab, we would actually take off our shoes. We would go in with, in a clean way. The room would have AC, and you would have to protect your floppy disks and other things. So there were, and today we go with our laptops anywhere, right? So, but quantum computers are at that initial stage today. But what is, exciting is that today, we have a lot of experience from our existing journey with technology, right? And also we'll see there are some other advantages that are there today, right? But quantum computers are at that early stage, right? So it was in the 80s that quantum actually started, research in this area started to build these quantum computers until 2016. From 1981 to 2016 is the phase that we call the experimental phase, where okay, so I'll just continue. Thought there was a question. So yeah, so 1981 to 2016 was what we call the experimental phase. But 2016, IBM made the first quantum computers available on IBM Cloud. So anybody could start accessing quantum computers over the cloud, start running programs. The following year, the open source programming language Qiskit was also released. So we are now in this stage called the NISQ, or what is the full form is the noisy intermediate state quantum, right? So what does that? We have quantum computers that we can use, but these quantum computers are noisy. Okay, they are noisy in the sense that they interfere. There is decoherence, which means that the qubit cannot hold its state for very long. It holds it only for a fraction of a second, and then neighboring qubits also interfere with each other. So there are a lot of things to be figured out, okay, before we reach that stage of fault tolerance. Okay, so today's classical computers they've been in this fault tolerant state for a long time, right? So they do error-free computation, whereas the quantum computers, there is error in the qubits. Okay, so until we reduce that error. So error correction is one of the hot areas of research on quantum computers today, right? So are there any questions so far, or do we take questions in the end? Maybe we can take a few questions at this point if there are.
Sure. We could take a few questions now. So a question which had come up earlier was, how much is one CPU here? So would you go, maybe you could go into some detail there.
So remember that, the information that the bit encodes, right? It encodes, in zeros and ones, right? Whereas the qubit, because of the superposition states that you can place them in, right? So the same number of, I forget now the calculations, but with a few hundred qubits, you reach a level where, with a few hundred noise-free qubits, you reach a level where the biggest supercomputer with the largest, with as many, let's say, bits as there are, objects present in the atoms present in the universe, even that large a computer will not be able to do the same level of computation as these few hundreds of qubits, right? So that's where because you're able to put them in that superposition state, And as I said, there is entanglement, there is interference. So as a result, what happens is the power is exponential with the bits, with the qubits, right? And that's the power we cannot reach with bits as it is, right? So that's sort of the wishy-washy answer, but we in subsequent sessions we can go into more details of those.
Sure. We'll keep an eye on the chat for questions, and then we can look at them as time comes around.
Okay, sure. Yeah, thanks. So how is the industry reacting to this, right? So given that, this technology is so disruptive, it has so much potential to disrupt. And so how is the industry beginning to mobilize resources? What is it doing, right? What are industry players, different companies in India and abroad, what are they looking at, right? What are the kind of applications they're looking at? And in that word cloud, many of you had put a lot of these, what you thought are the good applications, right? So let's look at, how the industry itself is shaping, right? So we are seeing applications across the board, right? Whether it is agriculture, whether it is image processing, whether it is energy, manufacturing, whether it is airports, logistics, and whether it is, drug discovery, pharmaceuticals. A lot of these areas, people have begun to explore how quantum computers can play a role and what is that advantage that they can bring, right? Because as we saw, Shor's algorithm shows that factorization is much faster. Grover's algorithm shows that search is much faster. So people have started looking at other algorithms in machine learning, optimization, chemistry, and various other fields to see what are those application areas where we are going to start seeing that advantage, right? And the question you just asked, at what point does that do the qubits give you that advantage over the bits? So we'll see a little bit of that, right? So there are several use cases that we are seeing, right? So some of the areas, the broad areas we are seeing: finance, logistics, optimization, chemistry. So in finance, we are seeing, option pricing, customer segmentation, fraud detection, portfolio optimization. Chemistry has some very interesting things people are looking at. Did you know that making fertilizers is one of the most polluting things today? But it's very important for us because we needed to grow our crops to ensure that there is enough food for humanity. But the process of making these fertilizers is a very dirty process, right? It involves polluting the environment, right? The air. New battery materials. A lot of research is now ongoing into how electric vehicles are going to be coming, right? So in these electric vehicles, a lot of that, the battery places a lot of importance. A lot of you talked about space travel. But for space travel, we are always looking at new materials which can withstand the different, things that the spaceship is subjected to, right? Protein folding, a lot of drug discovery. So all of this can, get affected by quantum, right? In the way that we are able to look at new materials, new compounds, new molecules, and also logistics and optimization, right? So we are seeing more and more. So there was recently a request for proposal from New South Wales Transport, where in the next 5 years, they want to transform how, they do transportation in that state, right? In Australia. So how do you, route vehicles? How do you ensure that, the vehicles are transporting optimally? And India has also started what is called the Gati Shakti I don't know if you've heard about it, where we are looking at, how India can optimize transportation across trucks, railway, aircraft, waterways, ships, and all of these, right? So how do you ensure that, because a lot of our crops, I don't know if you know, but a lot of our crops get wasted just getting transported from the farmer to the, the granary, to the storage location, to the processing plant. And often, rains come and a lot of these sheds are not covered. So a lot of the crop goes waste. So a lot of this can be, bettered using better logistics and optimization, whether it is to pick up, whether it is to plan where the truck should be going. What is the shortest route? You would all have heard about the traveling salesman problem. So is there an optimal way of solving that using quantum computers, right? So there are these multiple areas in which quantum computers have these potential uses, and people have started looking at this. And that's a very, all these are very hot areas of research, both as theoretical research and also as applied, as you try to run some of these algorithms on existing quantum computers, right? So IBM and Daimler, we have been looking at, new batteries, new materials for batteries, whether it is your lithium sulfur batteries. How do you improve their performance? So how do you do this, right? These are molecular level interactions. Can you simulate them on a quantum computer? Can you develop better, materials? How is it done today? These are all, you have to actually physically do it today, because you have to see how material A or molecule A and molecule B interact and what results in that, right? What is the result, right? But now with quantum computers, because they follow the same laws of quantum mechanics, you can actually look at simulating some of these interactions. You can look at modeling some of these molecules. You can find their, steady states. And that's a very, very exciting thing, because as I said, not only in batteries, but you can use the same kind of, simulations, whether it is in fertilizers, whether it is in drug discovery, in a lot of areas, right? Similarly, with ExxonMobil, we've been looking at, various things, whether it is for route optimization for ships, or whether it is for looking at thermodynamic observables. A lot of these things, again, we are looking at how do you, build these circuits. On the right hand side is a circuit. How do you build these? How do you run it on an actual quantum computer? And what kind of results can you observe from that? And is there some advantage you can get from doing this compared to classical computers? In the finance industry, so again, we've been looking at how do you compute the expected value of treasury bills, along with JP Morgan Chase. So a bunch of areas where we've been looking at, how do you take industry applications and how do you run it on quantum computers, right? And not, I showed you some examples here, but also in India, we are looking at various, along with various customers, we've started looking at various things of importance to India, right? So we'll talk a little bit more about that in the subsequent slides. But now let's go into, how is the academia reacting to all of this, right? So how does the academic world react to this? What has been happening in the academic world with respect to this? And I'll again, go back to one more, poll here. So what is the best way to learn quantum computing? I want to hear from you what you think, what are the best ways? Maybe you've already learned quantum computing, maybe you are on that journey or you want to start. So I want to understand from, you as to, what you think is a good way to learn quantum computing. And I guess some of this could be feedback for your professors also. because I know you learn a lot of high technology things. So hands-on, simulation tools, research, visual practical implementation, read, research and apply, Qiskit. Okay. Okay, so find a good teacher. Okay. Hands-on with Qiskit, project-based. Okay, so I see that a lot of you are already experts at some of this, right? So you seem to know, what is the way for you to learn this. How do you, gather information? How do you actually start using that information? And how do you do projects? And what do you do with this, right? So very, very, very good, so I see that you are already on a good path. And okay, get experience in real small practical problems. Okay, very good. So I'm going to go back. Okay, so what is happening today in India, right? So there are several courses have started, whether online, whether in universities, whether they are master's program, bachelor's programs, and many centers have also come up in different universities across India, right? Okay, so and I saw somebody had mentioned Qiskit. So Qiskit is IBM's open source, software development kit for quantum. You can download it, you can start using it. There are already existing libraries for machine learning, nature, which includes physics, chemistry, biology, finance, optimization. So multiple areas, right? So there are existing application libraries that you can use. There is also a textbook that you can use, which is an open source textbook. And you can actually go and start learning, Qiskit programming, right? There are also, these quantum courses which are there. So there are courses from, for example, that recently, last year, end of last year, in August, September, October. So there was this course jointly with IIT Madras that we had offered on NPTEL. There were over 10,000 registrations. There was an MTech program that started in ISC in 2021. For I think 20 slots, they had 1,000+ applications, right? So there is a new program that Birla Institute of Management Technology is also starting. So there are multiple. IIT Madras has an ongoing program which has been there for a few years now, which is an integrated program, right? Bachelor's and masters, right? So there are already many programs which are already there, and there are some new ones also coming, right? So every university today is looking at how do you build up, a program and offer it to students, because we are seeing that a lot of students are interested, right? When IBM runs these summer schools, our summer school program gets, from India, we get a lot of registrations, right? India is one of the countries from where the top number of registrations for the quantum courses happen, right? So there are a lot of, existing courses. You can go online, you can find a lot of free videos also. As I said, there is this free textbook from Qiskit. There are other textbooks also available. So it's actually very easy now to learn from the top. I saw somebody had written, find a good teacher. Yes, you can actually find all sorts of teachers online who have put very good videos. Peter Shore has a lot of videos. Vazirani has a bunch of videos on quantum computing. And there are many, many more, right? And many universities are teaching, and I wouldn't be surprised if your university, IIIT Kottayam also starts a program where you start offering quantum, right? Because you do have the faculty who are already experts at this, right? So there are many things that you can do, and there are multiple projects, because somebody said, you can learn from doing projects. So there are already, like I said, existing libraries for various areas. And the very interesting thing is that today you can access quantum simulators online for free, but so can you also access quantum computers for free. Okay, so you can actually run your programs on a real quantum computer. So IBM quantum computers are available over the cloud. You can write your Qiskit programs and run it. And if you do not know how to program, there is also a visual interface there where you can build gates by pulling, gates into and to create a circuit, right? But Qiskit, Qiskit is just Python. Okay, a lot of so whether it is Qiskit or any of the other programming languages, many of them are Pythonic. Okay, so which means that Python today is the most widely, used language today. Most students and, industry people already know this Python. So in terms of programming, you'll not find it hard at all, right? You'll be you can very easily start with the textbooks, and you can start building these quantum circuits. Many examples are given already. And as I said, the libraries are there, and there are some data sets. So you can easily start doing those projects. Okay, so you can be hands-on today. And as I said, there are many courses also. So all that is required on your part is that effort, right? So you just need to put that effort and learn, right? So that's what you have to do. So there is an ecosystem also that's building up. So there are, multiple universities, including, IIIT Kottayam, many industry players, the government, startups, research labs like our own, the IBM Research Lab. They're all coming together to form these hubs and to ensure that, research gets done and people are able to, learn the skills and start applying them on real problems, the industry problems, right? Like I told you, there are several industry problems that people have started looking at. So as a student, you can come to these hubs. What can you do? You can learn from the skills that pick up the skills, learn them, and start. Once you learn how to build these quantum circuits, you can then start applying them to industry problems, to the other scientific problems that are there, right? And a lot of people have actually written scientific papers just by, building algorithms and running it on these free systems, right? On these IBM quantum systems, which are available over the cloud. So you just do a search for IBM quantum experience. I think there is a new name for it, but you can actually find it. You can create an account there and start running your code on real quantum computers, right? So how is this technology improving, right? So we just saw, I told you that Shor's algorithm, shows that you can solve the factorization problem in a few hours on a quantum computer, something that will take billions of years. But is a quantum computer today there which can run that Shor's algorithm? So do you have such a quantum computer today? Okay, so actually we don't. So we don't have a computer, powerful enough to run Shor's algorithm for a large number. You can run it for small ones, but not large ones. So 2021, just a few months back, IBM released the first 100+ qubit quantum computer. Okay. Later this year, we are going to hit 400+, and 2023 will be the first 1,000+ qubit quantum computer. And this is where we believe, we are going to start seeing applications in industry where you're going to actually start seeing quantum advantage. So do you know what is quantum advantage? Quantum advantage is where a quantum computer can perform any industry problem or any problem much faster or in a much more efficient, cost effective way, right? So today there is no such problem that classical computers beat quantum computers, but with quantum supremacy, quantum advantage, we are going to see that quantum computers are going to beat these classical computers on some tasks, right? And those tasks, as we saw, of course, we saw there are things that classical computers will always be good at, but mathematically, the things we are showing, things like Shor's algorithm, Grover's algorithm, we are going to be able to implement them, and you're actually going to see real advantage and actually see that promised speed up that is there algorithmically today, right? So that's quantum advantage, right? So that's a term you need to remember, right? Because that's an important term. And we saw that we are in that NISQ phase, the noisy intermediate quantum computing phase. But once we reach, we are able to, solve the errors. Once we are able to do error-free computation on quantum computers, and as the qubits increase, we are also going to now see what is called the quantum volume increase. So what is quantum volume? Quantum volume is a function of the error rate and also the number of qubits. So you can keep on increasing the qubits, but if the errors on the qubits are high, then they are of no use, right? So the quantum volume actually measures how effective your quantum computer is in terms of running quantum circuits, right? Is the error rate less? Are the number of qubits high, right? So I just told you that we have reached that 100 qubit number in end of last year. We will reach 1,000 in the next 2 years. And simultaneously, we are working on reducing the error rate so that those number of qubits are not useless qubits, but they are actually effective qubits that contribute to the quantum volume. The other very interesting thing is that quantum volume is doubling every year. Okay, so we are seeing that quantum volume is doubling, and that I'm sure you've heard about Moore's law. Moore's law stated that every 2 years the classical computer's power was increasing, right? It was doubling every 2 years, right? So the new Moore's law is the quantum volume, right, which has been doubling, and we are seeing that this trend is going to continue. So in the forecasts that we have, we actually are going to, IBM has forecasted this, that we will be showing that this quantum volume law is followed, right? So what is the way forward, right? So what's the way forward? How is everybody in India contributing to this? So you all know that India has become we are a software nation, right? So we have done very well in the software arena. We are, doing extremely well. We have large companies in software catering to not only Indian clients, but also the needs of others across the world, right? But you also know that, we missed making much impact when it came to hardware, whether it was in computing, whether it was in telecom, or any of the other technology areas, right? So, but the government and industry has taken note. So there are some changes which are happening now, right? So as I said, quantum involves multiple areas: quantum cryptography, quantum computing, quantum sensing, quantum communications, quantum hardware, and each of this will get impacted, right? Because there is rapid, development in these technologies, and what India must do is to match the pace, right? On the classical, we did not make much impact on any of these side things. We only made impact on the computing or the software aspects, right? So that's what most of our large companies have been great at, right? So whether it's TCS or any of these Indian large IT companies, they have leveraged that power of software and built these large solution providers, right? And the Indian government, what it wants now is that it has started what is called the National Quantum Mission, right? So in this National Quantum Mission, 8,000 crores has been budgeted for primarily these areas, right? All of these areas, Indian government has said that it's going to invest in this, and I think they have already started investing in this, in these technologies, because what we want to keep pace with the world and want to lead as a nation, right? But there are things which we have a huge advantage in, right? By 2024, India will have the largest number of software developers in the world, right? Today it is the US, but by 2024, it will be India. India will lead in the number of software developers, right? And as I said, we are a software nation. We have demonstrated a lot of success in that, whether it's in exports or local industry. We've shown that software development is our forte, right? But how did we reach there, right? So it's also important to look at that journey which we took, right? So the first, classical computers were built in TIFR in the 50s, and then the first, classical computer arrived in the IIT Kanpur in the year 1963. Okay, in this year, the IBM 1620 computer landed in IIT in Kanpur airport, and from Kanpur airport to IIT campus, it was carried on a bullock cart because the roads were bad, and it was people feared that if you took it in a truck, it will harm the computer because it had a lot of moving parts then. So they took it slowly on this bullock cart to the IIT Kanpur campus, right? This was the year 1963. So 2024 will have the largest number of software developers in the world. So we did great in software, maybe because of the efforts of IIT Kanpur and many of the educational institutions of that time like TIFR. But as I said, we missed a lot of the other buses like hardware, telecom, and many of the others, right? And to make it happen, there was a journey which India took. So many of you might not know these professors, but this Professor Rajaraman and Professor Mahabala were professors in IIT Kanpur in the 60s. And they actually wrote a lot of books on Fortran programming, on the theory and computing of computers, and they started degree programs. And in fact, I studied in the 80s and 90s, and that time we used the Fortran textbook from Professor Rajaram, right? So there were, many things that early professors did, and IIT Kanpur started the first MTech program in computer science in the 60s, and Narayan Murthy was from the second batch of that. TCS started in 1969, but FC Kohli, and before that, he was part of Tata, I forget which Tata, because not Tata consultancy services, which he started in 1969. But before that itself, many of the FC Kohli and many of the employees of that Tata, I think it was Tata Power or one of those, or Tata Energy or something. And they took a lot of these courses in IIT Kanpur they took these short-term and long-term courses taught by Professor Rajaraman and Mahabala, and they looked at how can you take Fortran, or how can you take whatever language there were, how can you take those and apply it to the problems of the industry, right? And that's how, the software journey started, right? But there was no professor who was, or nobody who took over the same thing for hardware in India. And that's why we did not become a hardware nation now, right? There are things that people are beginning to change, but this is the important, learning for all of us, that, IIIT Kottayam, a lot of the, educational institutions in India, you now have to take on this mantle that was taken by some of these pioneering professors in the 60s. I'm not saying IIT Kanpur was the only place, but I'm just quoting one journey, right? Because I use some of the textbooks by these professors. I know that some of these people like Narayan Murthy and Kohli studied there in Kanpur and actually went on to build large, computing institutions in India, right? So it is important for us also, not to miss any of the other things. As I said, computing is one aspect, but a lot of other things are also there. So it's important for us to focus on these, but computing is the easy one for all of you as students to begin your journey, okay? So as I said, you can all access quantum computers over the cloud today. All the programming language like Qiskit is open source. You can start running it on your laptop, see how quantum programs can be run, start learning this technology. When I graduated from my BTech in 1991, there were no jobs in computing at that time. So all of us, we learned programming, but there were no jobs. But 6-7 years later, the computing boom took off, the Y2K problem and all these things happened. And that's when India took off. There was this ready workforce in software, ready, trained by, all these professors, as I said, who were waiting to go and solve these industry problems on computers. And we became that software nation, right? So similarly, now today, unlike in 1963, when physically the IBM 1620 had to be installed in IIT Kanpur, and you had to do a lot of, even running a program used to be a physical thing at that point. Today, you can actually, as I said, access quantum computers over the cloud for free for education. All of you can actually, there are classical computers, there are simulators, and there are quantum computers. You can access all the three today over the cloud, right? You can actually run your programs.
Yeah,
So,
there are other solutions. Yes.
Yes.
Uh,
So, yeah.
I think that was a mistake. Please continue.
Okay, no problem. Yes. So there are multiple things that, each of you can actually go and do. As I said, there are many courses also that you can take, and I listed some of those previously. So I'm going to, just stop here by, concluding. Many industries have shown, surveys have shown that, quantum is going to have a substantial impact. Many businesses believe that the skilling area, the demand for quantum skills is growing. In India itself, we are seeing that there are a lot of jobs now getting listed for quantum computing. And, as I said, quantum computing, AI, classical computing, it's all going to come together, right? So you now have to build these, hybrid systems over the cloud, which will power these new enterprise workflows, right? And the other thing to note is that, so as I said, it's Pythonic, the language is Pythonic, but the thinking has to be different. As you start to develop the algorithms, you have to learn how to use superposition, how to use entanglement, how to use interference. So all of these things. So as Nobel laureate Bill Phillips said, using quantum principles to compute is actually as different from classical computing as a classical supercomputer is from an abacus, right? So it will take you time, it will take you effort, but it's not hard. It's something where there is already a community, there is a lot of material that is already available. So you can actually start on this journey, unlike, as I said, on the classical computers where people had to go to physical computers, do a lot of effort. Nobody owned a laptop that time. Today, people actually own laptops and they can run these programs. So thank you very much. So if you have any questions, feel free to email me, connect with me. You can take my contact details from Professor Lincy, and we are already working together on some problems together. So we'll be very happy to help you on your journey, to create and the very good thing about quantum is that it's not just about IT or computer science. There is a role for physicists, there is a role for chemistry people, there is a role for engineering students from other branches. So this is a truly multidisciplinary area. So thanks a lot. So I'll stop here.
So with this, we come to the end of today's webinar on preparing for the quantum era. I would like to express my sincere gratitude to Dr. Subramaniam for teaching us about quantum computing. I would also like to express my gratitude for Dr. Lincy and Vishnu Ajith, the coordinators of this session. Last but not least, I thank everybody who attended the session, and I hope you enjoyed this and found it to be informative and useful. With this, we close the session. Thank you very much.
Thank you all. Thank you, Venkat, for joining with us. Thank you so much.